Hello and welcome. Today I will discuss the evolution of radiation protection in the medical setting, using insights from the article, Radiation Protection for Medical Workers, by Boyce and colleagues. My presentation will briefly take us through the history, turning points, and challenges we face today in ensuring medical workers are protected from undue occupational radiation exposure. Radiation is an essential tool in modern medicine, but it poses risks. Medical personnel are the largest group that is exposed to man-made radiation occupationally. Advancements have drastically reduced doses, however, interventional procedures still present a notable risk. Let's explore how radiation protection has evolved. Radiation safety has not developed linearly, it follows a repeating pattern, which the article calls a spiral. Each time a new type of radiation or imaging technique is introduced, the same pattern plays out. It begins with discovery, then widespread application of that discovery, recognition of associated hazards, implementation of safety measures, and finally, optimization. Then the cycle starts all over again with the next innovation. This teaches us that radiation safety is an ongoing process and dynamic. Before X-rays were discovered, scientists were already exploring electricity and magnetism. Researchers like William Gilbert, Faraday, and Crookes laid the groundwork for later discoveries. Though radiation hazards weren't yet fully understood, there were already signs such as increased illness in uranium miners, suggesting things that weren't tangible could have a biological effect. During the late 19th and early 20th centuries, scientists and the general public alike were brimming with excitement over X-rays and radioactivity. Röntgen discovered X-rays in 1895, and soon after, Becquerel and the Curies uncovered natural radioactivity. These tools revolutionized medicine, but at this time safety was an afterthought. Operators soon began reporting skin burns, hair loss, and even death. Edison's assistant Clarence Daly was among the first to die from radiation exposure. It was during this time that the earliest protective ideas, like limiting exposure time and using shielding, began to emerge. X-rays played a vital role in World War I. They helped aid in the precise location of bullets and shrapnel on the battlefield. While X-rays were used in prior wars, the introduction of the Coolidge tube allowed more powerful and more easily portable machines. With these advances came new hazards. Medical personnel suffered burns and eventually developed leukemia due to inadequate protection. This era marked the beginning of organized safety efforts like establishing exposure limits and recommending lead shielding. These were the foundational steps in radiation protection, including the realization that a standardized unit of measurement was needed. It was during this era that the Röntgen Society began their Committee on Röntgen Measurement and Dosage, and the British Röntgen Society initiated recommendations for the protection of operators, including collimation, shielded X-ray tubes, and the necessity of trained practitioners. Between world wars, committees in the US and the UK were formed to develop exposure guidelines. The American Röntgen Ray Society formed the first committee on X-ray protection. Röntgen became the standard unit for radiation measurement, and film badges were introduced by Edith Hinckley Quimby and by Robert Landauer to track individual exposure. During this era, the First International Congress of Radiology requested that a committee on X-ray units be set up, later becoming known as the International Committee on X-ray Units. Several years later, the Second International Congress of Radiology launched the IXCRCP, the International X-ray and Radiation Protection Committee, now known as the ICRP. Though the dose limits set at the time were still high by today's standards, the idea of a regulated monitored work environment was taking shape. This era was a key turning point in formalizing radiation safety. The Second World War brought about a massive leap in nuclear science, due to the Manhattan Project, a program to make the first atomic bombs. The development of these bombs led to the first long-term studies which still influence radiation protection today. During this time, radiation protection, or health physics, emerged as its own discipline. Scientists realized the importance of controlling internal and external exposures. When the first nuclear reactor operated in Chicago in 1942, the early recommended dose limits formed the initial recommendations of protection. Protective guidelines continued to become more structured. Notably, Edith Quimby developed a checklist to ensure that radiation use was justified and optimized, principles that we still follow today. In the post-war period, radiation medicine boomed. Hospitals used X-rays, cobalt machines, and radioactive tracers regularly. Absorbed dose and tissue weighting factors were now being taken into consideration. During this era, the protective practices became consistent and expected. The use of lead aprons, shielding walls, and specialized training became standard. The ALARA principle, as low as reasonably achievable, was introduced to stress the reduction of radiation exposure while still ensuring quality care. From the 1970s onward, the focus turned toward refining and enforcing existing protections. The ICRP revised dose limits to reflect cancer risk data. New medical technologies like PET, CT, and fluoroscopically guided interventions brought new safety concerns. At the same time, dosimetry and monitoring tools improved. This era emphasized making sure that both the patient and the practitioner receive only the minimum amount of radiation necessary. This chart highlights an encouraging trend, a significant drop in occupational dose over time. In the early 20th century, workers might receive 50 to 70 millisieverts a year. Today the average is under 1 millisievert, except in high-exposure specialties like interventional cardiology. This decline in occupational dose shows how effective our present-day protections are, but it also reminds us that certain roles remain at greater risk and need focused safety strategies. Despite the progress, new challenges constantly arise. Interventional radiologists and surgeons are exposed to scatter radiation near the patient. PET and CT introduced both high-energy photons and short-lived radionuclides. Some professionals using these tools aren't radiologists, so they may lack formal radiation safety training. This shows us we need cross-disciplinary education and protocols that fit specific procedures and work environments. Looking ahead, radiation safety must stay proactive. Emphasis on justification will continue, making sure every exposure is medically necessary, and optimization, refining procedures to reduce dose. There is growing use of real-time dosimeters and data analytics to monitor exposure. Further research into the biological mechanisms of radiation damage will help refine limits and protective strategies. The future depends on integrating new technology with a strong culture of safety. In summation, radiation protection has evolved in response to both innovations and risk. The spiral model helps us to understand how each new development prompts a new round of safeguards. Today's protections are the result of over a century of learning, often the hard way. And while current exposure levels are much lower, emerging technologies and roles means we can never become complacent. Ongoing education, interdisciplinary collaboration, and a strong safety culture are essential. Congratulations, you made it to the end of the presentation. I will now award you with a bonus slide. Reading the article for my presentation and learning about just how much Edith Quimby did for our field, I was surprised that I hadn't heard more about her. In a profession where radiation safety and innovation are so critical, it's remarkable how much of that foundation was shaped by her work. What really stood out to me is that she wasn't just a scientist. She was a trailblazer at a time when women in science faced serious barriers. She carved out space in a male-dominated field and left a lasting mark through her research, her mentorship, and her determination. I admire strong women who push boundaries, and I wanted to dedicate this slide to honor Edith Quimby. Her work continues to protect patients and inspire professionals like us, even if we didn't learn about her in school.